Hello everyone. In this video we will continue examining topic 5.3, electric cells, and in particular we will focus on secondary cells. So there's a distinction you need to know between what are called primary and secondary cells. A primary cell can only be used once before being discarded. The chemicals undergoing the reactions provide the EMF, or can only sort of be fully reacted once, and then after that, the cell is discarded. Secondary cells can be recharged and used more than once. Most human beings would call this a battery and a rechargeable battery, but this is where we are. So, how do you recharge a secondary cell? Well, the answer is remarkably straightforward, particularly given what we've already discussed about quote-unquote miswired EMFs, or EMFs wired in the quote-unquote wrong direction. So what you do is you use an external source of potential difference to drive current, quote-unquote, the wrong way through the cell or the battery. And this, if it is the right sort of cell or battery, will run the chemical reactions in reverse. And so once you've fully recharged it, you've sort of separated those chemicals in the cell again, if that is possible, if it's a secondary cell, then you can use that cell moving forward, okay? So in this cell to the right, this is a 12-volt battery being used to recharge a 2-volt secondary cell. And if you apply Kirchhoff's second law here to the full loop for the different resistors, you can derive a current of 0.625 amps for this particular setup. You can then calculate the power generated in the battery as 12 volts times 0.625 amps, which is 7.5 watts. And the power dissipated in the external resistors in the circuit, okay? And then the leftover power is the power that is being delivered to the cell. This is the charging power. And if you've ever looked at a USB port or, a charging brick, they'll be labeled with their charging power, almost always given being plugged into an external USB or into the wall itself. But in either case, you're using the external source to drive current, quote-unquote, the wrong way through the battery in order to charge it. As you discharge cells, there are some interesting, or at least a couple of important facts to know about sort of how cells discharge. Two cells with the same electrochemistry, so the same chemicals inside, will provide the same EMF with the same internal resistance. But they can provide that current for vastly different times, depending on the volume of the chemicals involved. And this idea, the fact that some batteries can be used for a lot longer to provide the same EMF or the same current, is known as the capacity of the battery. And it's what we think of when we think of secondary cells charging, right? If they're charging, we're increasing their capacity. It is fundamentally related to the total amount of chemicals that are separated and which can undergo reactions. So the capacity then is formally defined as the total charge a cell is able to provide. But this total charge a cell is able to provide is often written in a slightly confusing but more useful way. It's often written as the product of a particular current and a time, and the units are almost always amp hours, okay? So if a cell can provide 40 amp hours, which is fundamentally the same thing as a charge unit, but written as 40 amp hours, then the idea is that it could sustain a current of 2 amps for 20 hours, or a current of 1 amp for 40 hours, or a current of 4 amps for 10 hours. That's sort of how this works. It's worth noting this is in theory. In practice, both very high currents and low currents will cause difficulty in quantifying the total capacity, so you have to be a little bit careful. But within sort of the medium range, for whatever that means for that cell, that's how you interpret the capacity. Notice that a single amp hour is equal to 3,600 coulombs, which, remember, is actually quite a lot of charge. How did we get that? Well, note that an hour is 3,600 seconds. And so this is just a straightforward conversion from the definition of amp and hour. All right.